Ever wondered why Amish homes built for $12,000 stand strong after 100 years, while modern $400,000 homes need major repairs within 20 to 30 years? It's not luck or divine blessing, but superior materials, time-tested engineering, and maintenance culture that modern construction abandoned in pursuit of profit and speed. This is traditional building wisdom that creates structures outlasting everything the modern industry produces. Material quality. The foundation of Amish home durability begins with material selection, prioritizing quality over cost savings, using solid hardwoods and proven materials that last generations rather than engineered products designed for quick construction and planned obsolescence. The framing lumber is solid hardwood oak, maple, hickory, or ash milled from trees, cut on the property, or purchased from local sawmills at $2,500 to $3,500 for enough lumber to frame a modest 1,200 to 1,500 square foot home. This seems expensive compared to modern dimensional lumber costs of $8,000 to $12,000 for similar square footage. But the comparison is deceptive because Amish hardwood and modern softwood lumber are completely different products. The Amish 2x6 stud actually measures 2 inches by 6 inches, the full nominal dimension that gives the measurement its name. Modern 2x6 dimensional lumber measures 1.5 inches by 5.5 inches, having lost half an inch in each dimension to planing and processing. This half-inch difference means Amish framing uses 33% more wood by volume in each board, creating substantially stronger structures. The hardwood species themselves provide strength modern softwood cannot match. Oak and hickory have compressive strengths of 6,000 to 7,000 pounds per square inch compared to softwood species like pine or spruce at 3,000 to 4,000 psi. The hardwood framing is literally twice as strong as modern framing lumber, allowing the structure to support greater loads and resist deterioration over decades and centuries. The flooring is solid hardwood planks 3/4 to 1 inch thick, milled from the same oak or maple used for framing. The cost is $1,200 to $1,800 for flooring throughout the home, compared to $6,000 to $10,000 for modern engineered flooring or laminate products. The Amish solid wood floors can be refinished 10 to 15 times over a century or more, essentially lasting forever with proper care. Modern engineered floors can be refinished once or twice, if at all, before the thin veneer layer is exhausted and the entire floor requires replacement. The roof covering is standing seam metal, typically galvanized steel or aluminum, costing $3,000 to $4,000 installed for the entire roof. This metal roofing lasts 50 to 70 years without maintenance, compared to asphalt shingles costing $8,000 to $12,000, lasting 15 to 20 years before requiring complete replacement. Over a 60-year period, the metal roof requires 0 replacement, while asphalt shingles require 3 to 4 complete replacements, costing $36,000 to $60,000 total, 9 to 15 times the initial metal roof cost. The Amish avoid engineered lumber products, no oriented strand board, no particle board, no medium-density fiberboard, no laminated veneer lumber, no I-joists or engineered trusses. These products are manufactured from wood chips, sawdust, or thin wood strips glued together with adhesives that fail over time, particularly when exposed to moisture. The solid wood lumber used throughout Amish homes has no glue to fail, no layers to delaminate, and no hidden defects created during manufacturing. The long-term cost advantage of quality materials becomes clear over decades. The initial lumber savings from using modern dimensional softwood instead of hardwood, perhaps $5,000 to $8,000, is lost within the first 30 years when modern framing begins failing while Amish hardwood framing remains sound. The roof savings from asphalt over metal, perhaps $4,000 to $8,000, initially becomes a massive loss when asphalt requires replacement 2 or 3 times while metal continues performing. Free labor. The single largest cost in modern home construction is labor, typically consuming $150,000 to $200,000, or 50 to 60% of total construction budget for a $400,000 home. Amish construction eliminates this cost entirely through community labor donation, reducing the $12,000 material cost to the total home price. The barn raising brings 40 to 60 men from the church district to construct the home's shell in 1 to 2 days of intensive collective work. These aren't unskilled volunteers, but experienced carpenters, many of whom have participated in dozens or hundreds of similar projects over decades. The skill level equals or exceeds professional construction crews, combined with genuine care about quality, since they're building for a neighbor and friend whose home reflects on the entire community's reputation. The labor value, if compensated at market rates, would be enormous. 40 men working 12-hour days for 2 days represents 960 man-hours of skilled carpentry labor. At $25 to $30 per hour standard rates for skilled carpenters in rural areas, the labor value is $24,000 to $28,800 just for the 2-day barn raising. The interior finishing over subsequent 3 to 4 weeks adds another 100 to 150 hours of work from smaller crews, contributing another $2,500 to $4,500 in labor value. The total labor value donated is approximately $30,000 to $40,000 for a modest home, and could reach $80,000 to $120,000 for larger homes requiring more complex work. When this labor is combined with the $12,000 material cost, the true cost of an Amish home, if built with hired labor, would be $42,000 to $52,000, still dramatically less than modern construction, but more accurately representing the resources invested. The modern construction labor costs reach $150,000 to $200,000 for several reasons. Professional contractors operate businesses with overhead insurance, licensing, tools, vehicles, marketing, and profit margins that must be recovered through labor charges. The work proceeds slower with smaller crews, typically 4 to 8 workers rather than 40 to 60, extending the timeline from days to months and multiplying billable hours. The lack of community investment means workers have no personal stake in quality beyond contractual requirements and whatever professional pride they maintain. The community labor system works only because of reciprocal obligation. The 40 men helping raise the barn today know their own sons will need homes in the future, and this same community will provide labor then. The family receiving the home participates in barn raisings for others throughout their lives, paying forward the labor they received. This creates a labor pool of essentially infinite size that can be drawn upon without cash payment when needs arise. The efficiency of mass simultaneous labor cannot be replicated by hired crews. When 40 men work together, the framing that would take a 4-man crew 2 weeks is completed in 1 day. The coordination and momentum of that many skilled workers accomplishing visible progress hour by hour creates quality and speed impossible with conventional construction scheduling. Foundation engineering. The Amish foundation approach uses post and beam construction on stone piers rather than the concrete slabs or full basements common in modern building, creating structures that are simultaneously simpler, cheaper, more durable, and easier to repair than contemporary foundations. The foundation piers are hand-dug holes reaching below the frost line 36 to 48 inches deep, depending on climate, filled with stones and capped with large flat stones supporting wooden posts. The digging is manual labor requiring no excavation equipment, just shovels and strong backs. A crew of 6 to 8 men can dig 20 to 30 pier holes in 1 day, preparing the entire foundation for a modest home. The material cost is minimal, essentially zero if suitable stones are available on the property or from neighboring farms, or perhaps $500 to $800 if stones must be purchased and delivered. This compares to $15,000 to $30,000 for modern slab foundations, or $30,000 to $60,000 for full basements requiring extensive concrete, rebar, and professional excavation. The post and beam system places the home's weight on 6-inch to 8-inch square posts again, solid hardwood oak or locust, chosen for rot resistance that rest on the stone piers and rise to support the floor beams. The posts and beams create the structural frame, transferring the home's weight to the ground through the stone piers rather than through a continuous concrete foundation supporting every wall. The engineering is elegant in its simplicity. Each post supports approximately 2,000 to 4,000 pounds, well within the compressive strength of hardwood, which can handle 6,000 to 7,000 psi. The stone piers distribute this weight over 1 to 2 square feet of surface area, creating ground pressure of 1,000 to 4,000 pounds per square foot, easily supported by any reasonably firm soil. The durability exceeds modern foundations, despite the primitive appearance. Concrete foundations crack from freeze-thaw cycles, settling, and water infiltration, requiring expensive repair or replacement within 50 to 75 years. The post and pier system has no continuous structure to crack. Each pier is independent, and settling simply lowers that section slightly without affecting other piers. Barns built in the 1870s and 1880s still stand on original stone piers, now 150 years old and perfectly functional. The repairability is the system's greatest advantage. If a post rots at ground level after 80 or 100 years, the typical lifespan before even rot-resistant locust begins failing the home can be jacked up, the bad post removed, a new post installed, and the home lowered back down. This repair takes 2 to 3 hours and costs $50 to $100 in materials. Replacing a failed modern foundation requires lifting the entire home, demolishing the old foundation, pouring a new one, and lowering the home back down work, costing $20,000 to $40,000 and taking weeks. The crawl space created by raising the home 18 to 24 inches above ground level provides access for plumbing, wiring, and ventilation impossible in slab construction. It also protects wood framing from ground moisture and creates an air buffer insulating the floor from ground temperature extremes. Joinery techniques. The connections between framing members use traditional mortise-and-tenon joinery secured with wooden pegs rather than the nails, screws, and metal brackets holding modern structures together, creating joints that strengthen over time rather than deteriorating as metal fasteners rust and loosen. A mortise-and-tenon joint features a projecting tenon on one board that fits precisely into a mortise, rectangular hole cut into another board. The joint is cut by hand using chisels and saws, requiring skill and precision to create the tight fit necessary for maximum strength. When properly cut, the tenon fits into the mortise so tightly that it can barely be inserted even with moderate force, creating friction holding the joint together even before pegging. The wooden pegs, typically oak, hickory, or black locust dowels, 3/4 to 1 inch in diameter, are driven through holes drilled perpendicular to the joint, passing through both the mortise and tenon and locking them together permanently. The pegs themselves swell slightly when absorbing moisture and shrink when drying, creating a self-tightening effect that maintains joint integrity through seasonal humidity changes. The advantages over modern metal fasteners are substantial and accumulate over decades. Nails rust when exposed to moisture, losing holding power and eventually failing completely. Screws experience similar degradation, plus the stripping of threads from repeated stress. Metal brackets create hard points that concentrate stress at fastener locations, often leading to wood splitting at precisely the points meant to provide strength. The mortise-and-tenon joints distribute stress across the entire joint surface area, 10 to 20 square inches of wood-to-wood contact, rather than concentrating force at individual nail or screw locations. This distribution prevents the local failures that progressively weaken nailed connections until entire framing sections become loose and require repair or replacement. The joints actually tighten over time as wood seasons. Green lumber cut from recently felled trees contains 30 to 50% moisture that escapes over 18 to 24 months as the wood reaches equilibrium with ambient humidity. As this moisture leaves, the wood shrinks slightly. The mortise and tenon geometry means the tenon shrinks in dimensions, making it smaller, while the mortise shrinks in ways that make it tighter around the tenon. This natural shrinkage pulls the joint tighter rather than creating gaps, as happens with nailed connections. The 200-year-old barns still standing throughout Amish regions demonstrate the durability of this joinery. The mortise and tenon joints in these structures remain tight and strong despite 2 centuries of stress, temperature extremes, and humidity changes. Many of the original wooden pegs are still in place and functional, showing no signs of the rot or failure that affects metal fasteners within 20 to 50 years. The skill required to cut these joints by hand is substantial and represents knowledge that modern construction has almost completely lost. The Amish preserve this skill through apprenticeship boys, work alongside their fathers, and experienced craftsmen from age 12 onward, learning to cut joints by hand through hundreds of hours of practice. By age 18 to 20, they can cut mortise and tenon joints as precisely as their grandfathers, maintaining the skill transmission across generations. Wall construction. The wall framing uses true 2x6 studs measuring actual 2-inch by 6-inch dimensions rather than modern 1.5 by 5.5 dimensional lumber, creating walls with 33% more wood by volume and substantially greater strength and insulation capacity. The stud spacing is 16 inches on center, or closer, sometimes 12 inches on center for walls that will bear significant loads. Modern construction uses 24-inch spacing to reduce lumber costs, but this wider spacing creates weaker walls with more deflection under load and larger cavities, making effective insulation more difficult. The double wall construction creates total wall thickness of 12 to 16 inches compared to modern 6-inch walls. The outer wall is framed with 2x6 studs, 16 inches on center, sheathed with solid wood boards rather than plywood or OSB. An air gap of 4 to 8 inches separates the outer wall from an inner wall, also framed with 2x6 studs. The total assembly provides exceptional insulation, R35 to R45, compared to modern R13 to R19, and eliminates thermal bridging where wooden studs conduct heat through insulation. The insulation material is natural, either wool from sheep or cellulose made from recycled paper or plant fibers. These materials are loose fill, blown into wall cavities, completely filling the space without gaps or compression. Wool and cellulose provide superior insulation per inch compared to fiberglass bats and maintain their R value when damp, unlike fiberglass, which loses 50% of insulation capacity when containing moisture. The hand-fitted boards are carefully cut and fitted with minimal gaps. Modern construction accepts gaps and relies on caulking or foam to seal them, but these sealants degrade over time, allowing air infiltration. The Amish approach uses wood-to-wood contact with precision fit, minimizing gaps before any caulking is applied, creating air sealing that lasts as long as the wood itself. The structural strength of these walls exceeds modern construction dramatically. The actual 2x6 hardwood studs, 16 inches on center, create a wall that can support far more vertical load and resist far more lateral wind pressure than modern 2x4 softwood studs, 24 inches on center. This over-engineering provides safety margins that keep homes standing through wind, snow, and stress that damages modern structures. Roof engineering. The roof uses standing seam metal galvanized steel or aluminum panels with interlocking seams running vertically from ridge to eave, lasting 50 to 70 years without maintenance compared to asphalt shingles requiring replacement. Every 15 to 20 years, at costs exceeding the original metal roof installation. The roof pitch is steep 8 inches rise per 12 inches run, 812 or steeper compared to modern minimums of 412 or even 312 on some contemporary homes. The steep pitch sheds water and snow, rapidly preventing the ponding and ice damming that causes leaks in low-slope roofs. Water runs off before it can find entry points, and snow slides off rather than accumulating loads that stress the structure or melt and refreeze into ice dams at eaves. The overhang extends 24 to 36 inches beyond the wall plane compared to modern 12 to 18-inch overhangs or contemporary zero overhang designs. This deep overhang protects walls from rain, prevents water from splashing back onto the foundation, shades south-facing windows in summer, and allows moisture to escape from the wall cavity without being driven back inside by wind-blown rain. The rafters are hand-cut from solid lumber sized appropriately for the span and snow load, typically 2 by 8 or 2 by 10 members, spaced 16 to 24 inches on center. Modern construction uses engineered trusses, I-joists, or web trusses made from small lumber members connected with metal plates that reduce material costs but create complex structures with multiple potential failure points. The solid rafter approach uses more material but creates simpler, stronger roof framing with fewer failure modes. The absence of trusses provides usable attic space that many Amish families use for storage or even sleeping areas during hot summer months when upper-level rooms stay cooler. Modern truss designs fill the attic with web members, making the space unusable, wasting potential square footage that the home's foundation already supports. The metal roofing installation requires specialized skill, as panels must be cut precisely and seams must be formed correctly to create watertight interlocking connections. The Amish developed this skill through the same apprenticeship system that teaches other building trades, and metal roofing specialists within communities become known for their expertise and are specifically requested for barn raisings. The life cycle cost advantage is overwhelming. A metal roof costing $3,500 and lasting 60 years costs $58 per year. Asphalt shingles costing $10,000 and lasting 15 years cost $667 per year, 11 times more expensive annually. Over 60 years, the homeowner spends $3,500 for metal versus $40,000 for 4 asphalt shingle replacements, saving $36,500 while also avoiding the disruption and hassle of 3 roof replacement projects. The environmental advantage is also significant. The metal roof is essentially infinitely recyclable. When it finally requires replacement after 60-plus years, the metal can be melted and reformed into new panels. The asphalt shingles are petroleum products that become landfill waste, with billions of square feet of shingles discarded annually, creating environmental damage that metal roofing avoids. Window strategy. The window placement and sizing follows a minimalist philosophy, prioritizing thermal efficiency and structural integrity over views and natural light, with window area comprising only 15 to 20% of total wall area compared to modern designs featuring 30 to 50% glazing. The south-facing wall receives the largest and most numerous windows to capture passive solar gain during winter months when sun angle is low, 25 to 35 degrees above the southern horizon at midday. The low sun streams through south windows, penetrating deep into the home's interior and warming floors and walls that absorb and store this solar energy. The thermal mass releases the stored heat during evening and overnight hours, reducing wood stove fuel requirements. The east and west walls have minimal windows, perhaps one small window per room, providing morning or evening light, but limiting the summer heat gain that makes east and west-facing windows problematic. Summer sun at low angles and morning east and evening west shines directly through these windows, creating excessive heat that must be dissipated, while winter sun at these angles provides minimal, useful heating. The Amish window strategy recognizes that east and west windows create more problems than benefits and minimizes them accordingly. The north wall has the least window area, typically only 10 to 15% of the wall surface, with windows placed primarily for ventilation rather than light or views. North-facing windows receive no direct sunlight in winter, making them pure heat loss locations that drain warmth from the home. Summer north windows receive no direct sun but provide no cooling benefit over solid insulated walls. The minimal north glazing reduces heat loss dramatically compared to modern homes with equal window distribution on all sides. The windows themselves are handmade wood frames, typically pine or poplar for the frames, with oak or maple for sills that must resist moisture and wear. The cost is $2,000 to $3,000 for windows throughout a modest home, compared to $6,000 to $12,000 for modern vinyl or aluminum windows. The wood frames last indefinitely with proper maintenance. Periodic painting every 3 to 5 years protects the wood from moisture and UV damage.